In this video, we're going to talk about what vector spaces are and look at some examples. Okay, so I want to begin by reminding ourselves, so that Rn, so the set of vectors with n entries, so that set satisfies several what I call intuitive properties, basic arithmetic properties that we'd expect to be true. So for example, if x and y are vectors in Rn and c is a scalar, so c is some real number, I'm going to list out some of these properties that are true. When we add two vectors, when we add x and y together, that is still going to be in Rn. It's still going to be a vector that has n entries. Another basic property would be something like, oh, if I add two vectors, that's going to be the same thing as adding them in the opposite order, so doing y plus x. So this is something called a commutative property. It's a basic arithmetic property that's true about vectors in Rn. So there's a bunch of others. I'm just going to list out one more. So one other one, what about if I have c times x plus y in parentheses? So we can distribute a scalar over vector addition and get c times x plus c times y. So these are just a few properties, few of these intuitive properties, basic arithmetic properties that Rn satisfies, but there are several others. There are several other properties like this. Okay, so I want to generalize this now, because Rn isn't the only set of objects that satisfies these properties. There are other sets of objects that also satisfy them, and we call these sets vector spaces. Okay, so vector spaces. Okay, so let's give a more precise definition of what a vector space is. Okay, so here we go. All right, so let me zoom out a little bit so we can see this. Okay, so here's the definition. A real vector space, and I put the word real in parentheses because we could have complex vector spaces as well, although we won't really be talking about those in this class much at all, really. Mostly we're going to focus on just real vector spaces, and that means we're just limiting ourselves to looking at real numbers, is a set V with two operations. So one operation that's called addition, one operation called scalar multiplication. So when we multiply by scalars, we're going to be multiplying by real numbers, such that for all u and v, so u and v are in this set capital V, and all c and d in the real. So c and d are our scalars. The set needs to satisfy the following 10 properties. Okay, so we have this comprehensive list of 10 properties here. You'll notice that some of these are the properties that I just wrote at above that Rn satisfies. It turns out Rn actually satisfies all 10 of these. So for example, this first property says that, oh, if u and v are in the set V, when we add them together and get u plus v, that is still in V. This is actually one of the more important properties. This is called closure under vector addition. When we add two things that are in V in our set, we get a result that is still in our set. Okay, so another key property here is when you multiply u by a scalar c, that is still going to be an element in V. This property is called closure under scalar multiplication. So closure under scalar multiplication. Okay, and there are a bunch of other properties here that we sort of intuitively expect to be true. Like, for example, property 3 says that when we add elements, that addition is associative. So when you have 3 elements that you're adding the u and the v first, and then adding w is the same thing as if you were to add the v and the w first, and then add the u. One notational thing that I want to point out is I've written this symbol here that sort of looks like a backwards E, backwards capital E. That's a math symbol that refers to there exists. So property 4 is saying there exists an element 0, there exists a 0 vector in our set V, and that has the property that we'd expect, that when we add 0 to a vector u, we just get u. Okay, so a vector space is going to satisfy all 10 of these properties. So the thing that we've talked about so far in the class that we know as a vector space is Rn. So Rn, it turns out, is a vector space. But there are other sets of objects that also satisfy these properties, and we'll talk about some of them later in the video. Okay, so let's do an example. Okay, so here is our first example. So let's let V be the set of vectors, so I'm using set notation here, set of vectors that have two entries, x and y. So this colon, the way I read that, this is a math notational thing, the colon means the phrase such that. And it's used in set notation. So the way I read this is V is the set of vectors x that have two entries, x and y, such that x and y are both greater than or equal to 0. And the question is V a vector space? Okay, so how do we solve this? Okay, so if I want to show that this thing is a vector space, I need to show that it satisfies all 10 of those properties. It'll turn out that this isn't a vector space. And if I want to show something isn't a vector space, I just have to show that one of those properties doesn't hold. And usually we focus in on the most important of those properties. Okay, so I'm just going to list some of those. So if U and V are in my set, are in capital V, and C is a real number. The most important properties of V, for V to be a vector space, are, so one is 0. The 0 vector needs to be in V. So I sort of need to ask myself, is 0, let me word it like as a question actually. So is 0 in V? The second property is V closed under addition? So when we add U and V together, is that in V? Well, actually, let me use my element notation. Is this in V? And then also, is it closed under scalar multiplication? So is C times U, so when I multiply U by some real number, is that still going to be in V? So usually if we're going to show that something is not a vector space, we try to show that one of these three properties does not hold. Okay, so to get a feel for what this is saying, let me draw a picture. So we're talking about vectors in R2. So I'm going to draw my 2D plane. And x and y both need to be greater than or equal to 0. And that is this portion of the plane. So it's the first quadrant right here. Okay, and x and y are allowed to be equal to 0, which means I can be on this part of the x-axis, and I can be on this part of the y-axis. So just by looking at this, I know that 0 is going to be in V. 0 is part of this. It's this corner. So I'm not going to be able to show that property number 1 is not true. So here's the property that's not going to be true. Let's say I were to take some vector in my set. Let's say I call this vector U, and let's just let this be the vector 1, 1. I'm going to try to violate the scalar multiplication closure property. I'm going to multiply U by a negative number. I'm going to multiply by negative 1. So if I multiply U by negative 1, then I get the vector negative 1, negative 1. And the thing is, I needed this result to still be in my original set. I needed it to be in this blue first quadrant region, but it's not. This is not in my set. It's not in that blue region. And because it's not, sad face, that means we have a violation. This means that this violates the fact that C times U is supposed to be in V. In other words, my set is not closed under scalar multiplication. So because just one of the properties is violated, if even one of the properties is violated, our set is not a vector space. This is not a vector space. Okay, so just to recap the key takeaways from this. So I want to note two things. If I want to show a set V is a vector space, we must show that it satisfies all 10 of those properties that we listed before. And that can take a while, although most of them are usually pretty intuitive in terms of why they're true. But if I want to show a set V is not a vector space, and to abbreviate vector space, sometimes I'll just write V dot S dot. We just have to find one property that doesn't hold. Okay, and that's what we did in this example. Okay, so let's start to talk about some things that aren't just Rn, that aren't just vectors. Okay, so I'm going to recall something from our previous knowledge, maybe from middle school or high school, about polynomials. So polynomials, I'm just going to write a polynomial as P of t. They have the form, so P of t equals something like a, so the way I say this, instead of saying a sub 0, is we usually say a naught. So a naught plus a1 times t plus a2 times t squared plus dot 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 plus an t to the n. So polynomials look like this. So in this polynomial, my variable is t, and then the numbers a0, a1, comma, dot dot dot, comma, an, they're real numbers. So they're elements of the reals. Those are the coefficients of some of my terms. Okay, and n has to be greater than or equal to 0, and it's got to be an integer. Now let me say n is an integer. It's got to be an integer, and it's got to be non-negative. Okay, so let's do a couple of quick examples to make sure we are comfortable with this. So if P of t is 7 minus 6t squared plus 10t to the 5, this has this form. This is a polynomial. So this blue thing is a polynomial, and when we have a polynomial, we can talk about its degree. So we say that this polynomial has degree 5. And recall that the degree is the highest power with a non-zero coefficient. So what I mean by the non-zero coefficient is, technically if I didn't have this condition about the non-zero part, I could have said, oh, like I have 10t to the 5, couldn't I just tack on like 0t to the 100 to that? So wouldn't that mean the degree is 100? So according to this definition, we don't allow that because we ignore any terms that have a coefficient of 0. Okay, so now for this green polynomial, or quote unquote polynomial, q of t equals this thing right here. So this one is not a polynomial. That's why I kind of caught myself earlier there and said polynomial in quotes. And it's not a polynomial because in a polynomial, the powers have to be non-negative integers. But I have a 1/2 as one of my powers here. So this is not a polynomial since the exponents must be non-negative integers for it to be a polynomial. So q of t is not a polynomial, but p of t was. So q of t is actually something called an algebraic function. Okay, so now that we've sort of done this brief review, let me give you guys a definition. Okay, so here's the definition. So when n is greater than or equal to 0, I'm gonna introduce some notation. I'm gonna write p. So the way I read this is I say Pn. Pn is the set of polynomials of degree at most n. So Pn is going to represent the set of polynomials of degree at most n. So for example, let me just write out a few examples of polynomials that are in P2. So P2 would be polynomials of degree at most 2. So one example is I could just have something like 4t squared. That's a polynomial. It has degree at most 2. So this is in P2. But I could have something like 7 minus t. That's a polynomial. It has degree 1, but that definitely falls into the category of at most 2. So this is in P2. I could also have something of smaller degree. I could have something just with a constant term, like 7. We actually say that this has degree 0. This is degree 0 because this is technically 7 times t to the 0. So the highest power of t here is actually 0. But that still is in P2, because it's still a polynomial of degree at most 2. So it turns out that Pn is a vector space. So let's do an example where we look at that. Okay, so here is the next example. Pn is a vector space, it turns out. To show it, I would need to show all 10 of those properties that we've talked about. So I'm just going to show that it satisfies closure under vector addition and closure under scalar multiplication. And I'm going to leave for you guys to think about, well, why does it satisfy those other 8? But the other ones are actually more intuitively true. They're actually easier to show. Okay, so how do we solve this? Okay, so what I'm going to do is I need to take 2 things in Pn and then add them together and show that's in Pn still first. So let's start to write some stuff. So let's let P of t be a polynomial in Pn. So that means it looks something like, all right, a naught plus a1t plus dot 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 plus an times t to the n. Okay, and so this is something that's in Pn. It's a polynomial of degree at most n. And I'm going to let q of t also be an element of Pn. But q of t may have different coefficients from p, so I'll call those b naught, b1t plus dot 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 plus bn t to the n. So this is also in Pn. Okay, so that means that all ai and bi are real numbers. And then I'm also going to let c be a real number. I'm going to introduce c so that when we talk about this scalar multiplication, we have that in place. Okay, so let's check these 2 properties. So to check to see if it's closed under vector addition, and in this case with my set, the elements aren't vectors, they're polynomials. So I'm going to be adding polynomials here. What I want to know is, if I add p of t to q of t, is that also going to be in Pn? And if it is, it's closed under addition. Okay, so to do that, let's add these 2 things. So let's take the first polynomial, a naught plus a1t plus dot 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 plus an t to the n, plus the second polynomial, which was b naught plus b1t plus dot 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 plus bn t to the n. And if we add these together, I can group like terms together. So let's put the a naught plus the b naught together. Those are the constant terms. And then let's group the terms that have a t. So these are the ones that have a t. So let's factor, if we factor out the t, we're left with an a1 plus a b1 in the front. And if I keep going like this, finally I can look at the terms that have a t to the n. And if I factor out the t to the n from those 2 terms, the coefficient is going to be an plus b to the n. So when I add 2 polynomials, it ends up looking like this. But this is still a polynomial of degree at most n. So this is still in Pn, which means property number 1, closure under vector addition, holds. This is satisfied. Okay, so let's look at the second property. Okay, so now what I want to ask is, if I take an arbitrary polynomial like p of t, and I multiply that by some real number, some scalar, c, is that still going to be in Pn? And if it is, if it's still in Pn after I multiply by c, it's closed under scalar multiplication. Okay, so let's write this in green again. Okay, so this time I'm taking c, multiplying it by p of t, which was a naught plus a1t plus dot 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 plus an times t to the n. So if we multiply this, we have to distribute. So we'll get c times a naught plus c times a1 times t plus dot 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 plus c times an t to the n. Okay, so I get this after I distribute the c in. But this is still a polynomial, and it has degree at most n. So this is an element of Pn. Okay, so that means my set Pn is closed under scalar multiplication. So property number 2 is also true. So like I mentioned before, Pn, the set of polynomials of degree at most n, also satisfies those other 8 properties that we've talked about. And I'm going to leave it to you guys to think about why. Okay, but the other 8 are easier to see than the ones that we just did. And the ones that we just did weren't too bad at all. Okay, so next, I want to end this video by listing out some common examples of vector spaces. So we've seen 2 at this point. We have seen Rn, and we have seen Pn. But there are many, many others. So I want to list out a few for you guys. Okay, so let's zoom out a little bit so I can look at all of the ones that I have here. Okay, so the third example is when we talk about all real valued functions that are defined on what I call a fixed set. So for example, so what real valued means is when I plug in a number into it, when I plug in a number into my function. So here I'm plugging in a real number. This is my domain. Real valued means that when I plug in that number, I get out a real number. So this R represents the codomain. So the set of functions whose domain is R and whose codomain is R, that is a vector space. I could also talk about functions whose domain is a closed interval, and the codomain is the reals. This is the codomain, and that is also going to be a vector space. Okay, in the next example, I'm introducing some notation. So I'm writing C, and then in parentheses, I'm writing R. And what this represents is the set of continuous functions, f from R to R. So the domain is R, and the codomain is R. Okay. So when in example 5, all of the integrable functions, where the domain is the interval from a to b, the closed interval, and the codomain is R. So integrable, if I can integrate them, so they're using some calculus here, those form a vector space. The set of complex numbers form a vector space. And just in case you're curious, the symbol for complex numbers is I write a C, and then I put this extra vertical line here. So it's similar to like my notation for the reals, where I put this extra line, or even this symbol for like the polynomials of degree at most n, where I put this extra line. I put the extra line for those complex numbers. Another one we'll see is if we write capital M and then subscript n by n, this is the set of n by n matrices. So we can do things like add 2 matrices together, or multiply a matrix by a scalar, by a real number. And it turns out, under those operations, the set of n by n matrices is a vector space. Okay, but there are many, many more examples. But these are some. These are some examples of sets that satisfy those 10 properties that we've talked about that a vector space satisfies.